So we're going to pick up where we left off with the standing waves homework and jump to number 7, which is a nice biophysics application. So we have a diagram of the inner ear and the outer ear, and we have an ear canal where sound waves come in, right, strike the eardrum, cause vibrations. And this is essentially a closed pipe. It's a model of a closed pipe. The ear itself, the outer ear, is kind of a collection of waves. It's like a megaphone, collects waves and funnels them to here so that you get a higher intensity normal. And then what you can do is you can get standing waves produced based on the length of the ear canal, and that's what our ear are going to be most sensitive to. And that's what this question is asking. So the hint here was, what type of tube does this approximate? It approximates a closed tube. So why do we care? Because we know from previous ones, if we draw a closed tube, right, like this, the standing waves look like that. Okay, that sideways champagne glass. And the important thing that comes out of that is the wavelength of that standing wave is 4 times the length of that tube. In this case, the tube being 2.5 centimeters. So I'm going to got to convert that to meters. We don't want to leave that as is. Actually, I'm just going to do this all the numbers later. So that's going to be 4 point, excuse me, that. And so the frequency, the first one that occurs, is simply going to be the speed of sound, which is given, I think. Yeah, in a warm ear, so it's a little faster than normal because your ear is warm, divided by 4L, and for that you get the answer of about 3,500 hertz. And then for the second, so if we were in class, I'd play you a spectrum of sounds, and you'd note, without me changing the intensity, around 3,000 to 4,000 hertz, it sounds particularly loud. That's a resonance effect. That's a standing wave being formed based on the depth of your ear canal. Okay, so the next harmonics is going to occur, again, is not the second harmonic, because there are no even harmonics in a closed pipe, the third harmonic. So F3 is equal to 3 times F1, so that's just thrice this, or at about 10,500 hertz. Okay, some multiple choice. Standing waves in open pipe are the result of, or in any situation, doesn't even have to open pipe, is you have to have the reflection. Okay, waves are coming in from a source, they hit a barrier, a boundary, they bounce off, and they interfere with the incoming waves. And if the timing is just right, you get standing waves, which are an interference effect. So that's superposition is the way of talking about that. You probably could have figured this out by process of elimination, because we haven't talked about diffraction yet, nor refraction. Okay, so standing waves between successive notes, what has to be the same? Well, if I draw, let's say, a fixed string right here, and I'll draw a standing wave that looks like that, right? Here's a node and here's a node. So I'm looking at between it, is that what has to be, what's the same throughout is there's some driving frequency that's causing all this. So it's got to be something about frequency. But between successive nodes, okay, is different points in a wave are going to always be at different amplitudes, right? Points in a wave that are near the node are going to have low amplitudes. Points near the antinodes are going to have large amplitudes. So they can't have the same amplitude, so it's just going to be frequency. Amplitude and energy go together, so that's not why it's that. Okay, so the most difficult one of the multiple choice, really good problem, because we're going to do a lab on this with the tuning fork over a closed pipe. Is actually a pretty interesting experiment. Okay, you can derive the speed of sound from that, but that's not the question on here. So we have 2 separate standing waves formed, one between here and here, okay, and then one between the open air column and all the way down there. And the reason there's 2 different wavelengths is because we're just changing the effective length. So in this case, we're not changing the frequency. The frequency is determined by the fork itself, but we can create 2 different standing waves by changing the length, which changes the timing. And all the other problems, you left the length of the string or tube the same and changed frequencies to get different standing waves. This is an alternative way. So here's what we know in terms of how to solve this. Okay, so we have an expression for x and y. So what type of standing wave is going to curve at x? It's got to be a fundamental. It's the simplest standing wave. And since this is a closed pipe, we know that x has to be equal to okay, lambda over 4. In other words, we expect a quarter of a wave to fit into there because that's what the standing wave looks like. Now, if we go to the next harmonic, well, then that means we have to have another node here, and then another node here, and an antinode here. So without erasing this, I'm going to have, right, this is what my standing wave kind of looks like. All I've done is added another half wavelength. And I don't know if I've said this, but let me say it. If I have, let me say it again. When you go from one harmonic to another, don't care what the situation, all you're doing is always adding a half a wavelength to it. In fact, that's probably the easiest way to understand that. So if we start with a quarter of a wavelength for the first harmonic, then the next harmonic, which fits into Y, has to be a half a wavelength longer, or 3/4 lambda. Okay, so what are we trying to solve for? Wavelength in terms of x and y. So what I can do is I can subtract these two equations. I can say y minus x, therefore, is 3/4 of a wavelength minus a quarter of a wavelength, which subtracts to half a wavelength, as I mentioned before. In fact, if you know that fact, you could have gone right to that. And then we can solve for lambda. So lambda is then moved to 2 over y minus x. So the key takeaway I want you to understand here is you can create different harmonics by either changing the source frequency, or in this case, by changing the length of the air column, which is done by raising or lowering the water. The second thing I want you to take away is when you go from one harmonic to the next higher harmonic, it's always a half a wavelength greater, always. And that's a really important takeaway. Okay, as always, ask questions if there's things that are not clear still.